This video is about partial fractions with repeated linear factors. Now this is a continuation from the previous video, which was an introduction to partial fractions. This is now covering another case, namely when we have repeated linear factors. As we discussed initially, there are several cases with partial fractions and they're done a little bit differently. So we'll take a look at these. Now the following steps are just the general steps that are done really for any case. And so this will all look familiar. We have to check the degree of the numerator and denominator as step one. We have to factor the denominator if it's not already done, or if it's not impossible as step two. Then we're going to set up a decomposed rational equation in step three. In step four, we're going to clear the fractions of that equation. And then in step five, we're going to find the numerators of our new decomposed terms using one of these two methods, where either we substitute convenient values for our main original variable, or we create a system if that won't work for us. Now, case two, as we're discussing in this video, is when we have repeated linear factors. So notice in the first case, which was the previous video, we discussed just linear factors that were not repeated, they were distinct. Repeated means you have more than one of them. Of course, that's what it means to repeat. So we'll see an example of it. Now, as far as the notes for this case, we're going to understand that the decomposed numerators are going to be constant. That's actually the exact same as it was in case one, where we had distinct linear factors. So nothing different there. But then here's the new step for this repeated linear factors scenario. If we have repeated linear factors, then those of the denominator must occur in incrementing powers per decomposed denominator up through the original power of the linear factor. Now, that is a mouthful. Let's see if we can maybe look at an example to see what that all means. And then, of course, we'll note that multiple cases can occur within the same problem, and we'll just see that continuing to be true as we build up more and more cases. Let's consider an example where we want to find the partial fraction decomposition for the following rational expression. The numerator is 3x squared plus 49, and the denominator is x times x plus 7 in parentheses squared. All right, so let's just survey the nature of this rational expression, especially its denominator. And we'll go through our steps of determining what the degrees are, top and bottom. Notice the degree of the numerator is 2. The degree of the denominator would actually be 3, because if you consider that the binomial containing the x plus 7 is squared, that would really expand to a degree 2 polynomial, but then if you multiply that by x, it would end up degree 3. So really we have a degree 2 over a degree 3, which means we do not need long division here. We can skip that step, which means we can get right into trying to factor the denominator. But the way that this denominator is given, it's actually already factored. So let's just go ahead and copy down our problem. We have 3x squared plus 49 in our numerator. And then down below we have x times x plus 7 squared. So again, that denominator is already in factored form, which is fine. That just means we don't have to do that. So we'll go ahead now and just set up our decomposed equation. Now this is where the whole repeated thing is going to show up. One important question to consider to understand what's going on here would be, how many factors are in this denominator? Now that can be a somewhat of a tricky question, because it depends how you count them, right? The x that's in front of the parentheses counts as a factor. Notice that's a linear factor, but it's just a single x. Now notice the next factor is the x plus 7, but notice that it's squared. So this is what we're going to refer to as a repeated factor. Of course, it's linear. X plus 7 is linear, but the fact that it's squared means it's repeated, right? That would actually be like an x plus 7 times an x plus 7. It's repeating. Now, that could happen with any power higher than 2, of course. If you had to the power of 3 or higher, of course, that would also count as repeated. So we have one distinct factor, just the x, and one repeated factor. Both of them are linear, which means we're actually combining case 1 and case 2 in this problem. We said above that sometimes more than one case will show up, and that's what we're seeing here. We already know how to handle case 1, which is the single distinct linear factor of x. And that is, we're going to write its own fraction where it's in a denominator and its numerator will be constant. We'll just use the letter a to represent that. So that's what we've done already with case 1 in the previous video. Now, regarding the repeating linear factor that follows it, the x plus 7 squared, this is what's a little new. So we're going to do this. We're going to add another fraction, but start with only a single of that factor x plus 7. So it's not squared, it's just a single x plus 7. Its numerator will be some constant term. We'll just put a b there for now to hold the spot. Okay, and then what we said above about incrementing powers means this. We have to keep going because we have to make it all the way up to a power of 2 for that repeated factor, which means the next one, incrementing up, will be x plus 7, but this time it will be squared. Now, if you really want to see the incrementing vividly, of course, you could put that previous denominator as x plus 7 to the first. We normally wouldn't write it that way, but that makes it very hopefully obvious and explicit that we're just incrementing the powers starting from the single one, and then we step our way up to the highest we have. Now, we only have 2, so we'll stop at 2, but of course, if we had a higher power of that repeated factor, we would keep going, maybe a third or fourth, keep incrementing all the way up until we hit that highest power. Now, of course, these are linear factors, so the numerators are all going to be constant. I'll use the letter C for that last numerator. As you may recall, our next step would be to clear the fractions in this now decomposed rational equation. I'm going to multiply across the numerator by the LCD, which, remember, happens to be our factored denominator in this case. So if I multiply that all the way across, I'll end up with just a 3x squared plus 49 on the left side. And then on the right side, when I multiply, the denominators will be canceling with this LCD as it skips across. So like in the first fraction, the x in the denominator under the a will cancel with the x in the LCD, leaving us simply with the a and then the x plus 7 squared. Moving on, for the next term, we'll have a b, and then notice we have an x plus 7 in its denominator. That will cancel with one of the x plus 7s in the numerator, but that would still leave us with the x that's part of the LCD, and then one of the other x plus 7 factor. And then lastly, notice the last denominator, x plus 7 squared, would cancel with that factor of the LCD, leaving us just with a c and then an x. All right, so after clearing the fractions, which is what we have to do after factoring and setting up our equation like this, we're now at the place where we want to find a, b, and c. Remember, that's our goal. If we find those, we're done. And you'll recall that there's sometimes a method that works where you can pick convenient values for x. We saw this in our first case. Let's try it here again. Is there some value I could pick for x that when plugged in for x in this cleared fraction equation would cause all but one of my ABC variables to disappear, right? That's the goal. I have to find one at a time. If you think through this carefully, I think you'll find that when x is -7, some good things happen in that way. Now, if I pick x to be -7, of course, I have to plug it in for every x in this whole equation. So that will turn this into 3 times 49. That's the -7 squared plus 49. That's the left side of our equation. On the right side, notice if I plug in -7 for x, this first term will have a -7 plus 7, which is 0, which means that term will actually drop out. And actually the exact same thing would happen to the next term because of that x plus 7 factor there. That would turn into a 0. And then with our last term, if I'm plugging in x as -7, that will be just a -7c. Now this is good news. If we only have one of our ABC variables showing up, that means we can solve for it. So let's take this a step further. Turns out that 3 times 49 plus 49 is 196. So that's what we have on the left side. On the right side, we just have -7c. And so if we divide by -7 on both sides, we're just solving for c here, then we'll end up with c equals -28. All right, so we found one of our ABC values. That's good news. Now, of course, we have to find the others. Let's go ahead and recopy our cleared fraction equation You may recall we did this in the first case as well, because we want to try to do another step like we just did to get rid of some other, or to solve for some of the variables. So now we'll say 3x squared plus 49 equals a times x plus 7 squared plus bx times x plus 7. Okay, so we're just copying down what we had at that previous step equation, the cleared fraction version. We're just recopying the whole thing, except now we know that c is negative 28. So instead of saying plus cx at the end, we'll just say minus 28x. And here we have it. Now, what we have left to do is find a and b. It doesn't really matter which one we pick on first, but we'll want to try, if we can, to pick some value for x that when plugged in would cause one of those two terms to disappear, but not both. So again, think through carefully, and if you look at the terms, the b term has an x, a single factor of x in it, where the a doesn't. So if I let x be 0, that should help us out. Now on the left side of our equation, we'll have 3 times 0, which is 0 plus 49. On the right side, when I plug in 0 for x, I'll have just a times 7 squared, so that's really a 49a. Notice though, this middle term with the b will totally drop out thanks to that single x factor when x is 0. So I'll just put in a 0 there. And notice the last term, the minus 28x, would also drop out because when x is 0, that would disappear. Now, what we have left is simply 49 equals 49a. Everything else is a 0. Well, that simply tells us that a must be 1, which means now we've also found a. We only have one variable left to find, and as we've been doing here, to move on to that next step, we're going to recopy our cleared fraction equation. So we'll rewrite the 3x squared plus 49 equals, and then a, which we already found to be 1. So we can just write the 1 instead of the a. Of course, 1 in front of the x plus 7 doesn't even show up really. So really it's just x plus 7 squared is that first part. Then we're going to say plus bx times x plus 7. And then we'll say minus 28x. And so that's our, again, matching the previous steps equation that we had. We originally got that equation by clearing the fractions. Now notice there's only one variable left to find in it out of our original a, b, and c. So we want to target the b value. And since it's the only one left, we could actually pick anything we want for x to plug in. We'll just pick something simple like 1. You saw us doing that previously. If I plug in 1 for x in this equation, the left side should turn into 52 equals, it should be 64 plus 8b minus 28. Okay, that's just plugging in 1 for all the x's in the previous step. Okay, and it should give us this, which should allow us to solve for b. Okay, so doing that, getting b alone, should give us b equals 2 on this. And so there we have it. We now have found a, b, and c. And so if you think back to where we came from, our whole point was to decompose our original rational expression, and we had set up the decomposition equation, the rational equation, with those numerators. So really that's going to be our answer, but we're going to rewrite it with the new values for a, b, and c that we found. And so we'll just say really 1 over x plus 2 over x plus 7, and then minus 28 over x plus 7 squared. You may recall minus 28 is fine, or you could say plus and then put a negative 28 in the numerator. It really does the same thing. But this is our decomposed rational expression.